Hello there, and welcome to the Sleeping Physicist. If you're someone who likes to unwind by thinking about stars, matter, and the quiet structure beneath reality, you're very much in the right place. Tonight, we'll let our attention drift gently into real physics and real discoveries. Some of what you'll hear may sound surprising, but all of it is grounded in how the universe actually behaves. And if you enjoy these slow, careful explorations, you're always welcome to like and subscribe. But for now, get comfortable, let your body rest, let your thoughts loosen their grip, and let's begin. What are neurons made of according to quantum physics? When scientists first look at neurons, they do not begin with quantum theory at all. They begin with light and lenses, with microscopes that magnify thin slices of brain tissue until individual cells come into view. Under these conditions, neurons appear as delicate branching structures, each one shaped like a small tree, with long extensions reaching outward to make contact with others. They have a rounded central body, fine tendrils that receive signals, and a single long fiber that carries signals away. This is the level at which neurons are directly observed, touched by electrodes, stained with dyes, and counted. They are physical objects occupying space, responding to pressure, temperature, and chemistry, just like any other material structure. If you are listening from a familiar room, perhaps on a bed or a couch, those neurons are quietly present right now, arranged in dense networks, holding their shape without effort. This biological scale, neurons behave predictably. They grow, they maintain themselves, they respond to incoming signals, and they eventually wear down with time. This reliability is important because it allows the brain to function without constant instability. Nothing about a neuron at this level appears mysterious or undefined. It has a boundary, it has an inside and an outside, and it follows the same physical constraints as any other living cell. You could point to it, measure it, or even gently destroy it, and the rules governing that interaction would feel familiar. This is where understanding must begin, because quantum physics does not replace this picture, it quietly supports it. At a closer level, that solid biological picture begins to soften, not into mystery, but into detail. When the neuron is examined more closely, its apparent smoothness gives way to a crowded interior, densely packed with molecules in constant motion. The boundary that once looked like a clean outline is revealed as a membrane only a few nanometers thick, formed from two layers of lipid molecules arranged tail to tail. These molecules are not static bricks. They drift sideways, flex, and subtly rearrange, forming a living surface that can bend, seal, and selectively allow passage. This membrane is what gives the neuron its identity, separating inside from outside, while still allowing conversation with its surroundings. Embedded within this membrane are proteins of many kinds, each folded into precise shapes. Some act like gates, opening and closing to let specific ions pass. Others serve as anchors, receptors, or structural supports. Inside the neuron, long protein filaments form a flexible scaffold, giving the cell its shape while allowing it to grow and adapt. Between these structures flows water, not as an empty background, but as an active participant, surrounding every molecule, cushioning collisions, and enabling chemical reactions. The neuron is less like a solid object and more like a crowded city, where movement never stops but overall form remains stable. The most important travelers in this molecular landscape are ions. Sodium, potassium, calcium, and chloride drift through the watery interior and gather near membranes. Their motion is not random chaos, but carefully guided by concentration differences and electrical forces. When a neuron sends a signal, it does so by briefly allowing specific ions to cross its membrane, changing the electrical balance between inside and outside. This process feels electrical, but it is built entirely from chemistry. Molecules interact, proteins shift shape, ions move, and the signal emerges as a consequence. Nothing here yet requires quantum language, but every piece depends on deeper rules that chemistry alone cannot fully explain. It can help to imagine this molecular neuron as a harbor filled with countless small boats. The water is always moving, boats drift and bump gently, gates open and close along the shoreline, and yet the harbor itself persists, recognizable and functional. This image is not the explanation, but it allows the explanation to settle, because the key point is that neurons are made of ordinary molecules arranged in extraordinary ways, and molecules, no matter how complex, rest on something smaller still. As we continue, the question naturally shifts downward, asking what these molecules themselves are ultimately made of and why they behave so reliably inside a living brain. As we follow the structure of the neuron downward, the crowded molecular scene begins to resolve into something more fundamental. Every protein, every lipid, every drifting ion is itself an arrangement of atoms, held together in specific patterns. Carbon forms the backbone of complex molecules, hydrogen fills in bonds and shapes, oxygen and nitrogen add flexibility and reactivity, and trace elements like phosphorus and sulfur play crucial supporting roles. At this level, biology becomes chemistry, and chemistry becomes a story about atoms keeping their form over time. Atoms are small, but they are not abstract. They occupy space, they have mass, and they interact with one another in ways that are remarkably consistent. The reason a neuron can exist at all is because these atoms do not randomly fall apart or fuse together. Carbon reliably forms 4 bonds. Oxygen prefers 2. Sodium carries a positive charge. Potassium behaves almost the same, but not quite. These preferences are what allow membranes to seal and ions to move in controlled ways. If atomic behavior were even slightly unreliable, the careful balance inside a neuron would collapse almost instantly. At this scale, it becomes clear that neurons are not special materials invented by life. They are assemblies of the same atoms found in rocks, oceans, and stars. The calcium ion that triggers neurotransmitter release obeys the same rules whether it is drifting through seawater or crossing a synaptic terminal. What makes neurons remarkable is not the atoms themselves, but how they are arranged and constrained. Biology does not change physics, it makes use of it. You might imagine atoms here as finely machined components in a vast mechanism. Each piece has a specific shape and tendency, and when assembled in the right way, complex behavior emerges without any one part needing to understand the whole. This image helps only briefly, because atoms are not tiny gears. They do not click into place through contact alone. Stability and behavior come from something deeper still, something that does not behave like solid matter at all. Because when we ask what an atom is made of, the language of classical objects finally begins to fail. To understand why atoms hold together, why electrons stay near nuclei, and why chemical bonds exist in the first place, we must step into quantum physics. And it is here, quietly and inevitably, that quantum rules enter the story of neurons, not as exotic additions, but as the foundation beneath every stable piece of matter in the brain. When we look more closely at an atom, the familiar idea of a tiny solid sphere begins to dissolve. An atom is mostly empty space, with a small dense nucleus at its center and electrons existing around it in a way that defies everyday intuition. The nucleus contains protons and neutrons, tightly bound together, carrying almost all of the atom's mass. The electrons, much lighter, do not orbit like planets around a star. They, instead, exist as spread-out patterns of probability, describing where they are likely to be found rather than tracing fixed paths. This is the first place where quantum physics becomes unavoidable. Electrons behave both like particles and like waves, and their wave nature determines the size and shape of atoms. The reason atoms do not collapse inward, and the reason they maintain consistent sizes, is because electrons can only exist in certain allowed states. These states are not chosen by preference or design, but by the fundamental rules of quantum mechanics. The atom is stable not because it is rigid, but because it is constrained by probabilities that cannot be violated. Inside a neuron, every atom follows these same rules. The carbon atoms in proteins hold their shape because electrons occupy specific quantum states that allow bonds to form and persist. The ions that move during neural signaling carry their charge because electrons are absent or present in precise numbers. Even the softness of biological matter arises from the way electron clouds repel one another at very small distances, creating the sensation of solidity without true contact. What feels firm at the scale of touch is, at the quantum level, an intricate balance of forces and allowed states. It can help to imagine an atom not as a tiny object, but as a standing pattern, like a musical note sustained in space. The note does not have a sharp edge, yet it remains distinct and stable as long as the conditions are right. In the same way, atoms persist as patterns defined by quantum rules. This image is only a guide, but it points toward the central idea. Matter is not built from hard pieces stacked together. It is built from structured possibilities that hold their form over time. Because neurons are made entirely of atoms, and atoms are governed by quantum mechanics, neurons are, at their deepest level, quantum objects. But this does not mean they behave in strange or unpredictable ways at the scale of thought. Instead, it means that the reliability of neurons depends on quantum stability. The next step is to see how these quantum rules quietly shape the chemical bonds and tiny movements inside neurons, without ever announcing themselves as something exotic or fragile. Once atoms assemble into molecules inside a neuron, quantum behavior does not disappear. It becomes quieter, woven into the background of every chemical interaction. The bonds that hold proteins together exist because electrons are shared between atoms in precise quantum arrangements. These shared electrons do not belong fully to one atom or another. They occupy overlapping probability patterns that bind molecules into stable forms. Without this quantum sharing, the long chains of proteins that give neurons their structure would simply fall apart. Inside the neuron's membrane, ion channels offer a particularly clear example. These channels are proteins folded into narrow passageways, just wide enough for specific ions to pass. When an ion approaches such a channel, its movement is not governed by simple mechanical pushing. At the smallest scales, ions can sometimes cross energy barriers through a process known as quantum tunneling, slipping through regions that would be forbidden in classical physics. This does not happen often, and it does not dominate neural signaling, but it contributes subtly to the efficiency and reliability of molecular processes. Even the shapes of proteins themselves depend on quantum effects. The way a protein folds into a functional form is determined by a balance of electrical attractions and repulsions between atoms, all arising from the distribution of electrons. These electrons occupy quantum states that minimize energy, guiding the molecule into a shape that can persist in the warm, wet environment of the brain. If quantum rules were different, proteins might fold incorrectly or not at all, and neurons would lose their ability to function. You can think of this level as the silent choreography beneath visible motion, like a crowd moving smoothly because each person follows simple rules of spacing and balance. Molecules inside neurons behave coherently because quantum laws restrict what is allowed. No molecule needs awareness of the whole neuron. Stability emerges because the rules are firm and universal. At this point, it becomes clear that quantum physics is not something layered on top of neurons. It is the reason their chemistry works at all. And yet, when neurons send signals, what we observe is electrical activity that unfolds on a much larger scale. To understand how these quiet quantum foundations give rise to the electrical language of the brain, we need to look next at how neural signaling emerges from these underlying rules. When a neuron sends a signal, what unfolds looks unmistakably electrical. A wave of voltage travels along the neuron's long extension, rising and falling with precise timing. Electrodes can measure it. Screens can display it. This signal feels firmly classical, something that belongs to wires and circuits, rather than to quantum uncertainty. And yet, this electrical behavior exists only because of the quantum rules operating far below it. The electrical signal in a neuron arises from the controlled movement of ions across the membrane. Sodium ions rush inward, potassium ions flow outward, and the balance of charge shifts moment by moment. These ions carry their charge because of missing or extra electrons, and electrons behave exactly as quantum physics dictates. The forces that pull ions through channels are electromagnetic, rooted in quantum fields that determine how charges interact. Without the quantized nature of electric charge, there could be no smooth, repeatable neural signals. What matters here is scale. Each individual ion follows rules shaped by quantum mechanics, but the signal itself involves millions of ions moving together. Their collective behavior averages out the tiny uncertainties of individual particles, producing a stable, predictable wave. It is similar to how individual air molecules move unpredictably, yet sound waves travel smoothly through a room. The underlying randomness does not disappear, but it becomes irrelevant at the larger scale. This is why neural signals are reliable. The brain does not depend on fragile quantum superpositions to function. It depends on the consistency of quantum laws applied across enormous numbers of particles. The signal is classical in appearance but quantum in origin. Every spike of neural activity rests on an invisible foundation of allowed energy states, fixed charges, and stable interactions that never waver. Understanding this helps clarify a common confusion. Quantum physics does not sneak into the brain to perform special computations or mysterious tricks. It does something quieter and far more important. It guarantees that matter behaves the same way every time, even in a warm, noisy, living system. And that noise matters, because the brain is not a cold, isolated laboratory. It is a dynamic, thermally active environment, and this has profound consequences for how quantum effects can and cannot appear within neurons. Inside the brain, nothing is still. The temperature is warm, molecules are constantly jostling, and energy flows through every cell without pause. This environment is very different from the carefully controlled conditions where delicate quantum states are usually observed. In laboratories, quantum effects are often revealed by cooling systems close to absolute zero and isolating particles from their surroundings. Neurons exist at the opposite extreme, immersed in heat, water, and continuous interaction. This difference is not a flaw, it is a defining feature. Because of this warmth and constant motion, quantum states inside neurons do not remain isolated for long. When a particle interacts with its surroundings, its delicate quantum behavior quickly becomes entangled with countless other particles. This process, known as decoherence, causes quantum possibilities to collapse into stable, classical outcomes. In the brain, decoherence happens extremely fast. Any superposition or fragile quantum pattern is washed out almost immediately by collisions with nearby molecules. This is why neurons behave reliably rather than unpredictably. The thermal environment ensures that quantum uncertainty does not accumulate at the level of neural signaling. Instead, it is continuously smoothed away. The brain does not hover in a fragile quantum haze. It settles firmly into classical behavior, even though that behavior is built on quantum foundations. The warmth of the brain acts like a stabilizing force, preventing exotic quantum effects from dominating neural activity. You can imagine this like writing with a finger on the surface of moving water. Any fine, intricate pattern disappears almost as soon as it is formed, leaving only broad, stable motions. In the brain, microscopic quantum details dissolve into macroscopic reliability. This is not a limitation of nature, but a requirement for life. Without rapid decoherence, neurons would be too sensitive, too unstable, unable to maintain consistent patterns of activity. Understanding this boundary between quantum rules and classical behavior helps clarify what neurons are not made of. They are not sustained by long-lasting quantum superpositions or hidden quantum computations. They are made of matter that obeys quantum physics, while constantly being pushed into classical order by its environment. And this transition from quantum possibility to classical certainty is what allows neuroscience to function at all. With this boundary in mind, it becomes possible to see where quantum physics quietly hands responsibility over to classical neuroscience. The handoff is not abrupt. There is no sharp line where quantum rules stop applying. Instead, there is a smooth transition in which quantum behavior gives rise to stable, large-scale patterns that can be described without ever mentioning probability waves or uncertainty. This is the scale at which neurons live their working lives. At this level, the membrane voltage of a neuron behaves like a continuous variable. Ion concentrations can be measured, modeled, and predicted with equations that assume smooth flows rather than discrete particles. Synapses strengthen or weaken over time in ways that follow chemical kinetics and electrical feedback. These descriptions work because the underlying quantum events are so numerous and so rapidly decohered that their individual quirks cancel out. What remains is a dependable classical system that responds to inputs with consistency. This is why neuroscience can succeed without invoking quantum theory at every step. When researchers map neural circuits or record firing patterns, they are not ignoring quantum physics. They are benefiting from it. Quantum mechanics ensures that matter behaves reliably enough to be treated as continuous and predictable at the scale of cells. Classical neuroscience is not an approximation born of ignorance. It is an emergent description made possible by quantum stability. You might imagine this like looking at a beach from far away. Up close, every grain of sand has its own shape and position. Step back, and the beach becomes a smooth surface with gentle slopes and curves. Both views are correct. The closer view explains why the sand behaves as it does. The distant view explains how you can walk across it without sinking. In the same way, quantum physics explains why neurons can exist, while classical neuroscience explains how they function together. Recognizing this layered description helps prevent confusion. Quantum physics does not compete with neuroscience, it underwrites it. And with that clarity, we are prepared to address the ideas that often arise when these layers are blurred, especially claims that consciousness itself depends directly on unusual quantum effects inside neurons. At this point, it is natural for a certain idea to surface, one that has become familiar in popular discussions. Because neurons rest on quantum foundations, it is sometimes suggested that consciousness itself must arise from special quantum processes happening inside the brain. The appeal of this idea is understandable. Quantum physics feels deep and strange, and consciousness feels deep and strange, so it is tempting to imagine that one explains the other directly. But physics asks us to move carefully, guided by evidence rather than intuition. What quantum physics clearly tells us is how matter behaves at its smallest scales. It explains why atoms are stable, why molecules form, and why electrical charge is quantized. What it does not currently show is that neurons preserve delicate quantum states long enough, or in the right way, to perform uniquely quantum computations related to thought. As we have seen, the warm, wet environment of the brain rapidly destroys such fragile states. This makes sustained quantum coherence inside neurons extremely unlikely, according to everything we currently understand. This does not mean the brain violates quantum mechanics. It means it uses quantum mechanics in the same way all matter does. A neuron does not think because electrons are mysterious. It thinks, in the limited mechanical sense, because networks of cells exchange signals, adapt over time, and respond to their environment. These processes can be fully described using classical neuroscience, even though their material basis ultimately rests on quantum rules. It can help to picture this misunderstanding, like assuming that because the letters on a page are made of ink molecules, the meaning of the text must arise from the chemistry of ink. The chemistry matters because it allows the letters to exist, but the meaning comes from patterns, relationships, and interpretation at a higher level. In the same way, quantum physics allows neurons to exist and function, but it does not by itself explain awareness, intention, or experience. By letting go of the expectation that quantum physics must directly explain consciousness, something quieter becomes possible. We can appreciate the role quantum mechanics actually plays without burdening it with claims it does not support. This clears the way to understand what quantum physics genuinely contributes to our picture of neurons, not as a source of mystery, but as a source of stability and order beneath living thought. With those misunderstandings set aside, the real contribution of quantum physics comes into sharper focus. Quantum theory does not tell us how thoughts feel, or why memories carry emotion, but it does something more fundamental. It explains why matter can be organized at all, why complex structures like neurons can exist without dissolving into chaos. The brain depends on an extraordinary level of physical reliability, and that reliability is a direct gift of quantum laws. Quantum mechanics fixes the values of fundamental constants. It determines the strength of electric charge, the masses of particles, and the allowed energy levels of atoms. Because these quantities are stable, chemistry behaves the same way everywhere and at all times. A sodium ion inside your brain behaves exactly like a sodium ion in a distant star. This universality allows biological evolution to build increasingly complex systems without the ground shifting beneath them. Neurons are possible because the rules never change. At the scale of molecules and cells, quantum physics ensures that reactions happen with predictable probabilities. Proteins fold into the same shapes again and again. Ion channels open and close within reliable ranges. Membranes maintain their integrity despite constant thermal motion. None of this requires awareness or intention. It requires only that the underlying quantum landscape be consistent enough for patterns to persist. Life, including neural life, is built on that persistence. Seen this way, quantum physics plays a quiet but indispensable role. It is not the voice speaking thoughts into existence. It is the grammar that makes any physical language possible. Neurons do not need exotic quantum effects to think. They need atoms that behave the same way today as they did yesterday, and that dependability comes from quantum rules enforced at the smallest scales. As this understanding settles, the picture of neurons becomes both simpler and deeper. They are not mysterious hybrids of mind and physics. They are physical structures, assembled from quantum matter, operating at a scale where reliability matters more than strangeness. And this continuity, from quantum laws to living networks, leads naturally to a broader reflection on how there is no true break between physics and biology, only layers built patiently upon one another. When we step back and look at the full picture, something subtle becomes visible. There is no moment where quantum matter suddenly turns into life, and no instant where chemistry abruptly becomes thought. Instead, there is a continuous layering of organization, each level resting calmly on the one beneath it. Quantum rules give rise to stable atoms. Atoms assemble into molecules. Molecules organize into cells. Cells form networks. And from these networks, behavior and experience emerge without any new physical laws being introduced. Neurons sit squarely within this continuity. They are not exceptions to physics, and they are not elevated above it. Every electrical signal, every chemical exchange, every adaptive change in a neural network is carried by matter obeying the same quantum constraints that apply everywhere else in the universe. What changes from level to level is not the rules, but the patterns those rules allow to form. Complexity accumulates, not by breaking physics, but by using it fully. It can help to imagine this continuity, like a river flowing from a mountain. Near its source, the flow is shaped by the smallest features of rock and gravity. Farther downstream, the river widens, smooths, and begins to support ecosystems, movement, and reflection. The water has not changed its nature. It has only entered new contexts. In the same way, quantum matter flows upward into biology, carrying its rules with it, never needing to announce itself again. This perspective removes the need for hidden thresholds or special substances. There is no quantum spark that suddenly ignites awareness inside neurons. There is only the gradual accumulation of structure, feedback, and interaction. Thought, whatever its deeper nature may be, arises in a world already stabilized by quantum law. It depends on that stability, but it is not trapped at that scale. Seen this way, neurons are neither mysterious nor trivial. They are expressions of a universe that can organize itself across many levels without losing coherence. And when we ask what neurons are made of according to quantum physics, the most honest answer is also the most grounding. They are made of the same matter as everything else, governed by the same rules, arranged with extraordinary care by processes that never needed to understand the result. Even with this layered understanding in place, the story does not close. There remain questions that sit quietly at the boundary between what physics explains and what neuroscience is still learning to describe. These are not gaps where known laws fail, but regions where complexity outpaces our current ability to trace cause and effect in detail. Neurons follow physical rules, yet the collective behavior of billions of them interacting remains one of the most intricate systems we have ever studied. One open question concerns how microscopic variability influences large-scale brain dynamics. Even though quantum uncertainty averages out at the level of single neurons, small fluctuations can still shape long-term development, learning, and adaptation. Over time, tiny differences in molecular interactions may influence which connections strengthen and which fade. These effects do not require exotic quantum states, but they remind us that determinism and predictability soften as systems grow more complex. Another area of active research explores how biological systems maintain robustness while remaining flexible. Neurons must be stable enough to function reliably, yet adaptable enough to learn and reorganize. Understanding how physical matter achieves this balance using nothing more than chemistry and electrical signaling is an ongoing challenge. Physics provides the constraints. Biology discovers the strategies that work within them. There are also deeper questions about description itself. At what point does it become more useful to speak in terms of information, networks, or computation, rather than particles and forces? This is not a question about abandoning physics, but about choosing the right level of explanation for the phenomenon at hand. Just as we do not describe weather by tracking individual air molecules, we may never describe thought by tracking individual ions, even though both descriptions are grounded in the same physical reality. These open edges do not suggest mystery in the sense of hidden forces or unknown substances. They suggest patience. The brain is made of matter that obeys quantum laws perfectly, but it is arranged in ways that stretch our understanding of emergence and organization. What remains to be discovered lies not beneath physics, but above it, in the rich patterns that unfold when simple rules are applied again and again, across vast networks over time. And if you choose to continue from here, there are still more layers to notice, not new foundations, but deeper ways of seeing how matter, structure, and activity weave together into the quiet phenomenon of a working mind. As we move beyond the edges of individual cells, another layer of physics quietly takes over, one that concerns not particles or molecules, but large numbers acting together. This is the domain of statistical physics, where the behavior of many components becomes smoother and more predictable than the behavior of any single one. In the brain, this is where neurons stop being solitary objects and begin to matter as populations. Each neuron is influenced by countless microscopic events. Ions collide with water molecules, proteins vibrate, membranes fluctuate. Any one of these events is small and mostly insignificant on its own. But when billions of neurons interact, patterns emerge that are far more stable than the parts that compose them. Electrical rhythms synchronize. Activity spreads across regions. Signals reinforce or dampen one another. None of this requires new forces. It arises because large systems naturally average out noise. This averaging is a direct consequence of physical law. Statistical physics explains why. Temperature is meaningful even though individual molecules move unpredictably, and why pressure feels smooth even though it comes from countless impacts. In the same way, thoughts and perceptions unfold smoothly even though they are built from enormous numbers of discrete events. The brain works because it operates in a regime where collective behavior dominates over microscopic randomness. Seen from this perspective, neurons are not just quantum matter assembled into cells. They are components of a thermodynamic system, exchanging energy, maintaining gradients, and dissipating heat. The brain is not a delicate machine balanced on the edge of instability. It is a robust physical system that thrives precisely because it operates far from the fragile limits where individual quantum events would matter. This layer adds something important to the original question. Neurons are made of quantum matter, yes, but they are also made of statistics. Their reliability comes not only from quantum stability, but from numbers, redundancy, and feedback. And this collective stability is what allows higher-level descriptions like circuits, networks, and functions to make sense at all. From here, it becomes natural to ask how energy flows through this system, how neurons manage the constant cost of staying active, and how the physics of energy use shapes what brains can and cannot do. When neurons act together, they do not only exchange signals, they also exchange energy. Every electrical impulse, every restored ion gradient, every recycled molecule carries a physical cost that must be paid continuously. This is where the story of neurons meets the physics of energy flow, a layer just as fundamental as quantum mechanics, but easier to feel in the body. Neurons maintain their readiness by keeping ions separated across membranes, like water held behind a dam. This separation does not happen naturally. It is sustained by molecular pumps that consume energy, breaking down energy-rich molecules to push ions against their preferred direction of motion. Each time a neuron fires, a little of that stored separation is lost, and energy must be spent to rebuild it. Thought, in this sense, is not free. It is powered. At the deepest level, the energy that neurons use is governed by quantum rules. Chemical energy exists because electrons can occupy different energy states within molecules. When those states change, energy is released or absorbed in precise amounts. The molecule that neurons rely on most, often called the cell's energy currency, works only because quantum mechanics allows stable energy differences that can be tapped reliably. Without these quantized steps, energy transfer would be chaotic and inefficient. What matters at the scale of the brain is not the quantum detail itself, but the consequence. The brain consumes a significant fraction of the body's total energy, even at rest. This constant demand shapes how neurons behave. Signals must be brief. Networks must be efficient. Redundancy exists, but excess is costly. The physics of energy places quiet limits on how information can be processed, how fast signals can travel, and how long activity can be sustained. You might imagine neural activity like ripples moving across a pond fed by an underground spring. The ripples are visible and patterned, but they depend entirely on a steady, unseen supply of energy below. Quantum mechanics shapes the spring. Thermodynamics governs the flow. Together they allow the surface patterns to exist at all. This perspective brings us closer to a grounded understanding. Neurons are not only made of matter arranged by quantum rules, they are sustained by energy flowing through those arrangements, moment by moment. And this flow, constrained by physical law, shapes the possibilities of brains just as surely as their structure does. As energy flows through neural tissue, it quietly enforces limits on what brains can do. These limits are not imposed by biology alone. They arise from physics itself, from the same principles that govern all systems that store, move, and transform information. Neurons do not exist outside these constraints. They are expressions of them. Information in the brain is carried by physical states. A membrane is polarized, or it is not. A synapse is strengthened or weakened. A pattern of activity is present or absent. Each of these distinctions requires energy to create and maintain. Physics tells us that there is a minimum energetic cost to reliably distinguish one state from another, especially in a warm environment filled with noise. The brain must constantly spend energy to keep signals clear enough to matter. Because of this, neural signaling favors robustness over precision. Signals are not infinitely sharp. Timing is not infinitely exact. Instead, the brain relies on populations of neurons, redundancy, and averaging to represent information reliably. This is not a flaw, it is an adaptation to physical reality. Quantum mechanics sets the scale of energy levels. Thermodynamics sets the cost of maintaining order. Neurons operate comfortably within those bounds. These limits also shape speed. Signals cannot propagate infinitely fast without increasing energy cost and instability. The brain balances speed with efficiency, favoring pathways that are fast enough to matter, but slow enough to remain reliable. Even thought unfolds within these constraints, paced by ion movement, membrane recovery, and metabolic supply. Awareness feels immediate, but it is carried by matter obeying finite physical rules. It can help to imagine the brain not as a supercomputer, but as a living system tuned to the edge of usefulness. Like a radio signal transmitted through a noisy atmosphere, neural information does not aim for perfection. It aims for clarity under constraint. Quantum physics defines the smallest scales. Energy flow defines what can persist. Together, they shape a system that is powerful precisely because it is limited. Seen this way, neurons are made not only of quantum matter and flowing energy, but of trade-offs enforced by physical law. Thought is what happens when matter navigates those trade-offs successfully, moment after moment, without ever needing to escape the rules that made it possible in the first place. As neural activity unfolds, it does so in a particular direction. Signals propagate forward, energy is consumed, gradients are restored, and moments pass without reversal. This directionality is not imposed by neurons themselves. It arises from one of the most fundamental features of physics, the irreversibility of time in systems where energy is dissipated. At the microscopic level, many physical laws are nearly time-symmetric. The equations that describe particle motion work just as well forward as backward. But in systems like the brain, where enormous numbers of particles interact and energy is constantly transformed, a preferred direction, emerges. Energy flows from concentrated chemical stores into electrical activity and heat, and that energy does not spontaneously flow back into usable form. This is why a neuron can fire and recover, but cannot unfire in reverse. This irreversibility gives neural processes their arrow of time. Learning depends on it. Memory formation depends on it. A synapse changes because energy was spent to alter molecular arrangements, and returning to the previous state would require energy to be spent again in a different way. The brain's history is written into its structure through changes that cannot simply be undone. Quantum mechanics allows energy levels and transitions. Thermodynamics determines which transitions accumulate over time. You can think of this like footprints forming in soft ground. Each step is supported by the laws of physics beneath the soil, but once the ground is compressed, the path records where movement has occurred. Neurons leave similar traces in their connections and strengths. These traces are physical, energetic, and directional. They depend on time moving forward. This matters because it reminds us that neurons are not static objects, assembled once and left unchanged. They are processes extended through time, maintained by continuous energy flow, and shaped by irreversible change. Quantum physics supplies the building blocks. Energy flow animates them. Time gives their activity meaning and sequence. And with time woven into the structure of neural matter, the picture of what neurons are made of becomes richer still. They are not just arrangements of particles, but ongoing physical events, persisting only because the universe itself allows ordered change to unfold in one direction rather than another. As time moves forward through neural activity, the material of the brain does not merely repeat itself, it changes. Connections strengthen or weaken, structures subtly reshape, and patterns that once required effort become easier to evoke. This capacity for change, known as plasticity, is not an abstract feature layered on top of neurons. It is a physical process, carried by matter responding to use, energy, and constraint. At the smallest relevant scales, plasticity begins with molecules shifting their arrangements. Proteins are added to or removed from synapses. Receptors are inserted into membranes. Structural filaments grow, retract, or stabilize. Each of these changes is governed by chemistry, and chemistry rests firmly on quantum rules that determine which reactions are allowed and how likely they are to occur. Nothing about learning violates physics. It depends on it. What is striking is how gentle these changes can be. A small increase in activity at a synapse can slightly alter the probability that certain molecular interactions will occur. Over time, repeated activity nudges the system toward a new stable configuration. This is not a switch being flipped. It is matter settling into a different minimum, guided by energy flow and constrained by quantum-permitted states. The neuron remembers not by storing symbols, but by becoming something slightly different than it was before. You might imagine this process like a landscape shaped by water. Each rainfall follows the same physical laws, yet over time, channels deepen and paths form. The water does not intend to carve a river. It simply flows where conditions allow. In the brain, electrical and chemical activity flows through neural tissue, and the tissue responds by adjusting its structure. Memory is the accumulated shape of that response. Seen through this lens, neurons are not fixed components waiting to be activated. They are adaptable material systems, constantly reorganizing within the bounds set by quantum mechanics, thermodynamics, and time. Plasticity does not add mystery to the brain's composition. It reveals how deeply physical its adaptability truly is, and it invites a further question about scale, about how these slow material changes support fast, fleeting experiences that seem to arise and vanish in an instant. While the material of the brain changes slowly, thought itself can feel instantaneous. A sound is recognized in a moment, a memory appears without warning, a decision seems to arrive fully formed. This contrast between slow physical change and fast experience can feel puzzling, but it follows directly from how physical systems behave when many processes operate at different timescales. The structural changes that support learning and memory unfold over minutes, hours, or longer. Proteins move, connections adjust, and networks gradually reconfigure. These changes create a physical landscape that shapes how activity will flow in the future. Once that landscape exists, however, activity can move through it very quickly. Electrical signals propagate along established pathways in milliseconds, guided by structures that took far longer to form. This separation of timescales is a common feature of physical systems. The shape of a valley may take centuries to form, but a rolling stone crosses it in seconds. In the brain, quantum physics and chemistry build the valley walls slowly, while electrical activity flows rapidly within them. Experience lives in the motion, not in the construction, but the motion is only possible because the construction already exists. At the deepest level, even this rapid activity depends on quantum constraints. The speed of electrical signaling is limited by how fast ions can move and channels can open, all governed by molecular interactions and energy barriers. There is no shortcut around these rules. Thought feels immediate because the system is well prepared, not because it escapes physical time. This perspective helps dissolve another illusion. Conscious experience does not float free of matter, arriving faster than physics allows. It is the real-time expression of a system whose material has been shaped patiently by past activity. Neurons are made of quantum matter arranged slowly, so that experience can arise quickly when conditions are right. And with this understanding, the picture of neurons comes full circle. They are matter-obeying quantum law, organized by energy flow, shaped by time, and capable of supporting fleeting moments of awareness without ever stepping outside the physical world that made them possible. As this picture deepens, another quiet truth becomes visible. Nothing inside a neuron is assembled with foresight. There is no guiding blueprint aware of the final outcome. Order emerges because physical laws allow certain arrangements to persist while others fade away. Neurons are made of matter that naturally settles into structures that work, simply because those structures are stable under the conditions life provides. At the quantum level, particles follow probabilities. At the chemical level, reactions favor lower energy states. At the cellular level, structures that maintain function survive longer than those that do not. Across all these scales, the same principle applies. Configurations that dissipate energy smoothly and maintain internal balance tend to last. Those that cannot are dismantled by noise, heat, and time. Neurons exist because they are good solutions to the problem of remaining organized in a restless universe. This kind of order does not require intention. It arises the way crystals form when conditions are right, or vortices appear in flowing fluids. The neuron's shape, its signaling mechanisms, and its capacity to adapt are all expressions of matter exploring what is allowed and settling into what endures. Quantum physics defines the menu of possibilities. Energy flow selects what remains. You can imagine this like frost forming on a window. No two patterns are identical, yet all obey the same physical constraints. The frost does not know the shape it will take. It simply grows where conditions permit. In the brain, neural structures grow and refine themselves in the same quiet way, guided not by foresight, but by feedback and physical law. Seen from this angle, neurons are not extraordinary substances imbued with purpose. They are ordinary matter given time, energy, and the freedom to reorganize. Their complexity is not imposed from outside. It is invited by the universe's capacity to generate structure when simple rules are applied repeatedly. And this brings a final calm perspective to the original question. According to quantum physics, neurons are made of particles and fields behaving exactly as they do everywhere else. What makes them remarkable is not their ingredients, but the way those ingredients are allowed to assemble, persist, and quietly give rise to the fleeting phenomenon we recognize as a working mind. One more layer settles into view when we notice that neurons are never closed off from the rest of reality. They are open systems, continuously exchanging matter and energy with their surroundings. Oxygen arrives through the blood, nutrients diffuse into cells, waste products are carried away, heat is released into the body. A neuron exists only because it is embedded in larger physical flows that connect it to the planet, the sun, and ultimately, the wider universe. This openness matters because quantum physics does not act in isolation. The rules that govern particles inside a neuron are the same rules that govern particles everywhere, but the neuron's behavior depends on constant interaction with its environment. Without fresh energy arriving, ion gradients would fade. Without heat leaving, orderly signaling would dissolve into noise. The neuron's identity is maintained not by separation from the universe, but by continuous exchange with it. At the smallest scale, this exchange is carried by particles and fields. Photons released as heat carry energy away. Molecules diffuse across boundaries. Electromagnetic forces extend beyond the cell, linking charges across space. None of this feels dramatic, yet it is essential. The neuron is not a self-contained object. It is a pattern sustained by flow. You can imagine this like a whirlpool in a river. The whirlpool has a recognizable shape, but it is made entirely of water passing through. Stop the flow, and the structure disappears. In the same way, a neuron persists only because matter and energy move through it in carefully regulated ways. Quantum physics defines how that matter behaves. Larger-scale physics determines how the flow is maintained. This perspective completes the grounding of the question. Neurons are not special substances hidden inside the skull. They are open, dynamic arrangements of quantum matter, continuously supported by the same physical processes that light stars, drive weather, and sustain life across the planet. And in that sense, the material of thought is not separate from the universe. It is a small, temporary organization within it, held together for a time by rules that never needed to know what thinking was. As we let all of this settle, the question we began with becomes quieter and clearer at the same time. What neurons are made of, according to quantum physics, turns out not to be a strange or exotic answer at all. Neurons are made of the same particles and fields that make up everything else: electrons, protons, atomic nuclei, energy levels, and forces behaving exactly as they do throughout the universe. There is no special substance reserved for thought, no hidden ingredient added when matter becomes alive. What changes is not the rules, but the arrangement. Quantum physics provides a stable foundation: atoms that hold together, molecules that keep their shape, charges that behave predictably. Chemistry builds on that stability, biology builds on chemistry, and neural systems build on biology. Each layer depends completely on the one beneath it, yet expresses something new without ever breaking free from physical law. Neurons are not quantum machines in a dramatic sense. They do not balance on fragile superpositions or rely on mystery to function. They are reliable precisely because quantum uncertainty is tamed, averaged, and transformed into stable matter and smooth electrical activity. Thought arises not from exploiting quantum strangeness, but from being protected from it by scale, number, and constant interaction with the environment. Seen this way, the brain becomes less mysterious, but no less profound. It is a place where the universe's most fundamental rules quietly organize themselves into patterns that can learn, adapt, and respond. Neurons are open systems, shaped by energy flow, changed by time, and held together by laws that were already in place long before there were minds to wonder about them. And there is something gently grounding in that realization. The matter that thinks, listens, and understands is not separate from the rest of reality. It is continuous with it. The same physics that stabilizes atoms in distant stars stabilizes the cells carrying this moment of awareness. Nothing extra had to be added. Nothing had to be violated. Just matter, following the rules it has always followed, arranging itself for a while into something capable of noticing that it exists,